Hello and welcome to the screencast on looking at multiple regression and trying to interpret the partial regression coefficients. And again, it's not just a multiple regression problem that we're interested in, but sort of any linear model where we have multiple predictors and we're estimating them simultaneously, the parameters associated with those predictors simultaneously, and are trying to interpret them. So first, as always, we're gonna use a couple of libraries here. We're gonna use lattice for a few quick little plots, and then we're gonna be using some specific functions in both the ASBio and the car library. If you have not installed these libraries, remember to install them first. I'll just call them. And the other thing I should mention is I've changed one thing is now instead of having to have the data set on your computer right away, I'm downloading the data set that we're using directly from Dryad, so it should be a permanent link, so you can just use this link to grab the data. So as always, there's a few, although it's not super important for this first part, we will be changing some of the input variables to the right kind of classes. So we're changing temperature replicate. Oops, we didn't need to do temperature twice, my mistake. We're doing temperature and replicate two factors. Let me just do that. Okay. So as we discussed in class, when we're thinking about partial regression coefficients, or these parameter estimates that we get from a model, a linear model where we have multiple predictors, we need to remind ourselves that unlike the simple model where we have a single predictor variable, these will when we have multiple predictors, they will simultaneously adjust for any patterns of covariation among the predictors. So the parameter estimates can be quite different if the predictor variables themselves are correlated with one another. So let's think about an example where we have some simple model. Y is a function of three predictor variables, x1, x2, and x3. So we can say model y is model is a function of x1 plus x2 plus x3, simple additive model. What effectively is going to happen in terms of this linear model, the estimation procedure, effectively what the parameter estimate associated with predictor x1 will be the equivalent as if from running this full model that's still highlighted in blue would be the equivalent of first modeling the response variable y as a function of the other two predictors, x2 plus x3, and then also modeling x1, that predictor, as a function of x2 plus x3. And from both of those we will take the residuals. So we'll take the residuals from model 1, the residuals essentially of y after accounting for variation in x2 and x3, and similarly take the residuals from model 2. So in other words, the variation in x1 after accounting for the explanatory power, or the covariation from x2 and x3. So you can really think about this mathematically as it's effectively the influence of x1 on y conditioned upon x2 and x3 being already present in the model. And that's the idea, and we'll do a real example. So we're just going to remove any missing data for this example, and let's run this full model that we're interested in right here, lm.full, where we're accounting for variation in sex comb teeth, our response, as a function of femur, tibia, and tarsus length, which are three segments on the fruit fly leg. All right, so we run that. We're similarly going to also, for the moment, we'll focus on tarsus length as a sort of focal variable. Let's run the model as well, just with sex comb teeth as a function of tarsus. And for your information, the tarsus is in fact the structure on the leg which the sex comb teeth are present on. So we run those models. Okay, so now let's compare. We won't worry so much about the summaries, although feel free to look at them. Let's just take a quick look at the differences. Don't worry so much about the intercept for the moment. Just look at the tarsus length. So the estimate for the tarsus length for the full model is an estimate of 22.3, while the estimate for when we just model tarsus alone is somewhat higher, at almost 27. And if you want to look at the standard errors, we can actually just add up here at coef in each of these cases, so we can actually get a look at these. And again, we can sort of see that for the tarsus, even the standard errors are somewhat different for each of these, and not surprisingly, as soon as those are different, our t-values will end up being a little bit different, what have you. They're both, in this case, if we cared about such things, highly significant, but that's not the point. We're not getting the same estimate is the point. So what's going on? So one way of thinking about it is we can do a plot that may help a little bit. So here's a plot, and I'll shrink this down, of just looking at the relationship between sex comb teeth and tarsus. And there's some weak but positive relationship between these two. Oops, that's a little too small. We'll come back to that in a moment, though. What we want to think about is we actually want to, like we did above, or we described above, let's model first sex comb teeth as a function of femur and tibia. So we're going to account for all the variation in sex comb teeth once we've accounted for femur and tibia. And similarly, we're going to account for variation in tarsus. So tarsus will be our response in this case as a function of femur and tibia. Again, another additive model. So we'll run these two models. And now what we're going to do is plot. This may look a little ugly. Let me just straighten this out so it'll look a little clearer. So what we're going to do is plot those residuals of the two models. So residual of lm.d1, that's residual variation in sex comb teeth once we've accounted for femur and tibia. And the residuals here, lm.d2, well, that's residual variation in tarsus once accounting for femur and tibia. So we're left with all of the variation in sex comb teeth and all of the variation left in the tarsus length after having accounted for femur and tibia. So you can think about this as residuals for sex comb teeth conditioned on femur and tibia, and so on. And so we'll plot that, and we'll plot that lowest line just like we did before. And we can see here, and we'll just zoom into this, we still actually have a positive relationship. That might be even slightly clearer. You have to be careful once we've accounted for this. So this is essentially saying this is what's left. This is the relationship between sex comb teeth and tarsus once we've accounted for femur and tibia. And that's really what we want in this multiple regression problem. So if we fit this lm.partial, so again, we're doing just like we did before. We're going to do a regression of the residuals of sex comb teeth after accounting for tibia and femur, and the residuals of tarsus were residuals of tarsus after accounting for femur and tibia. So variation in sex comb teeth and variation in tarsus after accounting for those other covariates, and that's what we're modeling one on top of the other. Run that. We'll just call that lm.partial. And now if we look at the coefficients of those two, indeed what we see is here our slope is 22.37, so it's 22.37 times 10 to the 1, but 22.37, which is exactly what we got with the original multiple regression model. And again, if you would prefer and look at it in terms of the have standard errors and everything presented as well, there we go. We can see, yes, again, 22.37, standard error of 2.43. Here we get 22.37, standard error of 2.43. It looks like some of the significant digits are slightly different, but pretty damn close. And that's not hugely surprising since we did slightly different calculations all the way through, but they should be doing the same thing. Okay. And we could go through this and run the different models. Let's not worry so much about that for the moment. But what I want to make a point of is this plot, this lower plot we here. In multiple regression, we often talk about this as the partial regression plot or the added variable plot. So it's again just sort of saying the plot conditioned upon it. And in fact, in the CAR library, there is a function, avplots, which will do this automatically for all the variables. So in this case, we should get one for tarsus, tibia, and femur. So we'll get 3 different plots showing those relationship between sex comb teeth and each of the potential predictor variables, femur, tibia, and tarsus, conditioned on all other predictor variables. As we talked about in class, in addition to the coefficients, the parameter estimates that we get being adjusted for being adjusted for all other predictors in the model, we actually can use a partial coefficient of determination, which we'll discuss in class on Thursday, that allow us to essentially get an R squared for particular an R squared for each particular model. So up here we're going to run the model of sexcomb teeth as a function of tibia and femur, so in other words without tarsus. And what we do here for partial R squared, we excuse me, for the partial R squared, we compare the full model with the model without that term. And that gives us a number, 0.04. Well, what does that tell us, right? What's that for? What's that partial R squared telling us? Well, let's compare it to a couple of things. Let's compare it to, let's do a summary of lm.partial. Okay? Here again is our multiple R squared. So the R squared that we have for the model of sexcomb teeth regressed onto tarsus after having accounted for tibia and femur is 0.04, which is exactly what we get up here in that partial R squared. And we can compare that to two different things. First of all, the R squared for the full model, which accounts covariation for all of them, which is about, our R squared is about 0.09 or almost 0.1. And we can also compare it, I believe it was called lm.tarsus. We do the same thing, let's clear that up. We do summary lm.tarsus, we get something else. So if we do tarsus by itself, not correcting for the additional covariates, it looks like the amount of covariation we explained is about 8 or almost 9% of the variation. But when we adjust for those other ones, we see it's only about half of that, only about 0.4. So we realize that there's a great deal of correlation or covariation among these. And that's an important thing. So much like we can adjust the parameter estimates, we can do the same thing for variance accounted for. All right, and this is not only true for models with continuous predictors, but we can just as easily do this for models where we have categorical predictors as well. So here's a model where we have genotype and temperature, which are both categorical with 2 levels each. We can run them and get their summary models, and we get these, the intercept and genotypic temperature effects. Again, these are as treatment contrasts and the interactions. Make statements about them if we want, and with an R squared of about 14%. We can say, okay, well, how important is that interaction? Yes, it's significant, but does it add a lot? So let's run that same model. This time we're running it without the interaction term, so just the additive genotype and temperature effects. And we run this model, and the R squared is only about 9%. So we go from 9 to, what was it, about 14%. We can more explicitly say, well, how important is that interaction term by computing the partial R squared for those two different models. And again, that's saying basically about 5.5%. So that interaction term accounts, once adjusting for the main terms, accounts for about 5.5%. This is approximate, but it gives us some idea. All right, we're going to stop with there, and the next tutorial will be on following up with this, so you want to have the script open, but looking at how collinearity among the predictors influences our estimates in these models. Thanks.